For decades, we've seen this incredible story play out with technology. Our devices just keep getting faster, smaller, and more powerful, almost like magic. But underneath all that amazing progress, there's a crisis brewing. It's a threat so small you have to measure it in single atoms, but it's big enough to potentially stop the future of computing right in its tracks. We're talking about the silent killer of Moore's Law. And to really get it, we've got to think smaller than we ever have before.
And I mean really small. We're talking about the race to the angstrom scale. The whole industry is pushing past 3-nanometer chips, which are already just ridiculously tiny, and they're heading towards a world where a single angstrom is the name of the game. So what does that even mean? Well, an angstrom is basically the size of an atom. We've actually reached a point where the literal building blocks of matter are the new frontier, and, well, the new battlefield.
And that right there brings us to the core problem, what we're calling the atomic threat. See, at this unbelievable scale, those invisible enemies that chip makers have always fought, tiny defects, a little bit of contamination, they're not just minor annoyances anymore. They're not something you can just work around. They've become a fundamental wall, threatening the entire idea of Moore's Law.
So what exactly are we talking about here? An atomic level defect is, well, it's literally a single atom that's not where it's supposed to be. It could be a speck of an impurity, a stray particle, anything. Now, in the past, who cares, right? It would have been totally negligible. But on a chip built at the angstrom scale, a single misplaced atom can mess up the whole flow of electrons, causing the entire device to just fail. It's a tiny, tiny error with absolutely catastrophic results.
Okay, so you'd think an industry this smart, this advanced, would be all over this, right? But here's the twist. The real problem isn't a lack of technology. It's a mindset. It's this comfortable complacency. It's like the whole industry is stuck in its old ways of thinking, kind of seduced by these solutions that were good enough for yesterday's problems, but not for today's.
And a huge piece of this puzzle is the classic sunk cost fallacy. These chip companies have poured billions with a B, into their current equipment and all their processes. So admitting that those expensive tools just aren't precise enough anymore, that means writing off these massive investments. It's just so much easier to protect what you've already bought, even if it means you're sacrificing the future.
And this whole idea is backed up by decades of experience. The industry got really used to this slow, steady, predictable process of improvement. They call it the yield learning curve. And it's a perfect example of how one of the industry's greatest strengths, its mastery of gradual improvement, has now become its single biggest weakness. It's like a warm blanket, giving everyone this false sense of comfort, while masking the brutal new reality that the old methods are completely failing at the atomic level.
So instead of making a real fundamental change, what does the industry do? It develops what you could call a Band-Aid arsenal. These are all these clever but ultimately temporary little fixes designed to just manage the problem of atomic contamination instead of actually, eliminating it. So these fixes are things like, say, extended wet cleans, which just add more steps and more cost, but they never get you to true atomic level cleanliness. Or they use something called gettering layers, which is basically just sticking a material in there to trap contaminants. It's like admitting defeat before you even start. Another trick is over-specifying materials, demanding everything be ultra pure just to create a safety margin. It's an incredibly expensive workaround, but you see the common thread, right? None of these solve the problem at its source. And this little diagram just illustrates the result perfectly. It's this flawed, frustrating, reactive loop. A new problem pops up, slap a Band-Aid on it. The Band-Aid masks the real root cause. The company sees a temporary little improvement, they breathe a sigh of relief, and then they just wait. They wait for the next inevitable failure. It's a cycle of compromise, and it just can't go on forever.
And look, this isn't just some theoretical problem for engineers in a lab coat. This complacency, this reliance on Band-Aids, is already hurting the development of the crucial technologies that we are all counting on for the future.
Let's take gate-all-around transistors, or GAA FETs. You can just think of them as these tiny, vertically stacked switches. They are the absolute critical building blocks for any chip smaller than 3 nanometers. But because of their complex 3D shape, they have a massive surface area, which makes them super vulnerable to atomic contamination. And the result? Companies stuck in the old way of thinking are hitting major production delays and really bad yield problems.
And it's pretty much the same story with chiplets and hybrid bonding, this amazing idea of connecting smaller, specialized chips together like high-tech Legos. For this to work, you need atomically perfect connections. But trying to use your standard, old-school contamination methods for these advanced connections is just a recipe for disaster. It threatens the reliability of the entire system.
But maybe the most glaring example is high-NA EUV lithography. Now, this is the next really big thing in chip making, a super powerful new technology for making things even smaller. But it is so sensitive that the tiniest little defect on a silicon wafer can completely ruin the whole process. Without getting to atomic-level perfection, its incredible potential is just going to be completely wasted.
If you need one single fact to really understand the stakes here, this is it. A single invisible layer of oxide, we're basically talking about rust, at a connection point can increase the electrical resistance by orders of magnitude. We're not talking 10 or 20%. We're talking a factor of 100 or even 1,000. That is the difference between a chip that works and a very, very expensive piece of useless silicone.
So, what's the way out of this? How do we fix this? Well, the path to perfection, it starts with acknowledging a really uncomfortable truth. The old ways are done. They're obsolete. The strategies for controlling contamination that worked for the last 30 years are just not good enough for the angstroms era. Period.
And that is the really uncomfortable truth. The industry's entire philosophy has to change. That comfortable rhythm of making tiny, incremental improvements to systems that are decades old, it just cannot work at the angstrom scale. It's not enough anymore. It's time for a total, fundamental reimagining of how we control the manufacturing environment itself.
This new philosophy, it demands a complete overhaul. We need new metrology, the science of measurement, with tools that are precise enough to actually see atomic defects. We need brand new barriers that stop contamination before it even gets close. And it means embracing truly innovative solutions that go after defects at the source, instead of just trying to clean up the mess afterward.
So, at the end of the day, this brings the entire semiconductor industry to a massive fork in the road, a critical decision point. And the choices that these companies make right now are going to determine who leads and who gets left behind for the next decade of technology.
And the two paths forward couldn't be any clearer. On one side, you've got the comfortable path. Just cling to the old, obsolete ways and watch as your yields drop and your competitors blow right past you. And then there's the winning path. Embrace the massive challenge of atomic-scale precision, make the tough investments, and lead the charge into the future.
Which leaves us with one last big question. This change? It's coming. It's inevitable. The laws of physics pretty much demand it. But will the giants of the semiconductor world make this huge transformation by choice and proactively go out and seize the future, or will they be forced into it by the painful necessity of failure? The race to the angstrom scale is on, and being complacent is a price that absolutely no one can afford to pay.